Hello and welcome. In this lesson, we will be covering IT coupling snubber parametrization in detail. You will learn when snubbers are needed and why, and how to calculate them. Let's start. When IT coupling components are added to the circuit, topological conflicts can occur. As described in the topological conflicts lesson, these conflicts are solved by adding snubber circuits in parallel with a coupling's current source or in a series with a coupling's voltage source. In Typhoon HIL schematic editor, you typically don't need to add these circuits manually. Snubbers are embedded in the pre-built coupling components. Snubbers can take several forms: a resistor on either the current source or voltage source side, a series connection of a resistor and capacitor on the current source side, or a parallel connection of a resistor and inductor on the voltage source side. Additionally, snubbers can be fixed or dynamic. When a topological conflict is created after adding a coupling component, snubbers must be used to solve it. Topological conflicts in the circuit can be present through all switch permutations, or only in several switch permutations. Topological conflicts that are always present are solved by fixed snubbers. Conflicts that are present only during specific permutations of the switches should be solved by dynamic snubbers. In a nutshell, when they are enabled, fixed snubbers are included in every circuit permutation, while dynamic snubbers are added only when they are needed. To be more precise, when there is a direct degeneration of some component, the compiler will only include dynamic snubbers when the degeneration happens. Once you figure out which snubber type you have to use in your model, you have to insert a snubber value. Let's cover how to calculate them. Snubber parametrization consists of two general rules. The first one is that the time constant should be several times larger than the simulation step. The second one is that the overall impedance of the snubber on the frequency of interest, usually 50 or 60 Hz, should be sized to introduce small losses in the circuit, typically under 1%. This depends on the voltage level in the circuit and the total power that is transferred through coupling component. It is important to note that relative error introduced by the snubber depends on the overall power transferred through it. If nominal power is transferred through the coupling, the snubber's effect can be neglected. Meanwhile, if there is no power through the coupling, we will have a high relative error, since the only power flowing through is due to the snubber circuit. You can find a document with equations you can use in order to calculate snubbers in the Materials tab. Now let's look at when to use fixed or dynamic snubbers with a practical example. In order to find this example, please check the Materials tab. Here, we have two single-phase inverters connected in parallel. Since there are filter inductors, the voltage side of the core coupling element is rotated towards the inductors. Let's compile the model without snubbers. As you can see, we have warning that the voltage side of the coupling is degenerated. This warning appears since the core couplings are in parallel, and it means that voltage sources on the voltage side of the coupling are in parallel all the time. In this case, fixed snubbers are needed. They can be added by entering the component properties of the core coupling component. You can choose which snubber type you want to use, as well as if it should be fixed or dynamic. Let's now try with a fixed R snubber and then compile the model again. As you can see, by adding only a R snubber, the compiler warning disappears. If you notice the model is not stable when you run it with a fixed R snubber, you can add a fixed RL snubber instead in order to try to improve model stability. Now that we have resolved the voltage source degeneration, let's move on to the remaining warnings. These errors occur due to switch degeneration caused by the current side of the coupling. In that case, when all switches are open, some of them must be degenerated by the current source in the coupling, and we have to enable snubbers to avoid this situation. Since the topological conflict is present only in one switch permutation, we can use dynamic snubbers. Now we will add a dynamic snubber RC snubber on the current side of core coupling. To do this, we will follow the same process as before, but here we set fixed snubbers to false. When we compile the model with the dynamic snubber included, we can see that by adding a snubber to the current side of each core coupling, the conflict disappeared. Let's now open the battery inverter switching model from our microgrid example library in Example Explorer. This example demonstrates snubber usage in order to improve model stability. This simple example consists of the battery inverter component, which is directly used from the microgrid library. If we look what we have under the mask, we can see that there is a three-phase inverter, LC filter, measurements, and lastly a circuit breaker at the output. Let's go back to the root. Next to the inverter there is an inductive load, as well as a contactor in a grid, represented as a three-phase voltage source. Since the load is inductive, the voltage side of the core coupling component is rotated towards the load. As you can see, snubbers in this example are added by default, so now let's see the reason for that. Let's double-click on the coupling and then disable couplings. Now, if we compile the model without snubbers, but with the included coupling stability analysis, we will have the following warning. This error means that the core coupling is not stable. In this case, a snubber is needed to resolve the stability issue. Dynamic snubbers can be used to solve topological conflicts, but if a topological conflict is not present, as is the case in this model, enabling dynamic snubbers will do nothing. Because of that, we need a fixed snubber to improve stability. You can follow the general rules on snubber calculation that we mentioned before in the snubber parameterization documentation in the Materials tab. The snubber time constant should be several times larger than simulation step. In this example, we used a constant 20 times larger than the simulation step. The nominal power of the inverter is 1.6 MVA while the nominal line voltage is 480 volts. When we apply the corresponding equation, we get the following parameters for R and C. When we compile the model again, we have a message that everything is stable. Snubber parametrization sometimes can be complicated, especially when models are complex. As is explained in the previous lesson, one advantage of TLM couplings is that there is no need for snubbers and thus they are much easier to use. But there are situations when IT couplings are more suitable than TLM. IT couplings are recommended in power electronics applications while TLM couplings should be used in microgrid and power systems applications. With this lesson we covered how to parameterize snubbers for IT coupling when performing electrical circuit partitioning. The next lessons will be more focused on signal processing partitioning and device partitioning. So, see you then. Thank you for watching.